We are now going to discuss filtering in frequency domain. And for this discussion, we need to introduce a few concepts, Fourier series, Fourier spectrum, the problem of aliasing, also the different colors that the noise may have. We're going to talk about Nyquist frequency, and we're going to finalize with the example of transforms. So the idea behind Fourier series, and you have to realize that Fourier, this French mathematician and engineer, he was working with heat transfer, and he wanted to come up with the idea of how to model how the heat was being transferred from a rod that was very hot to a rod that was not hot. And then he came with the idea that we would think very simple today, that a particular function, or thinking in discrete terms, a data series with this argument tau that represents basically time. We know that can represent also space, can be expressed by the summation of several different waves. So in other words, a very complicated waveform can be decomposed into a series of simple waves, and he did that then by writing it down mathematically in a series that today bears its name. So what we have here is essentially the time series, and we have a polynomial that starts with the constant term, and then it grows from 1 up all the way to infinity. And we have, for each degree, we have coefficients, and we have a cosine and sine terms, and we have here the angular velocity omega, and is the summation count, and tau would be the time argument. So these coefficients, a sub 0, a sub 1, a sub 2, b sub 1, b sub 2, etc., they are known as the Fourier coefficients. And it's important to realize that the treatment of series as finite or infinite will lead to different results. So in practice, of course, we are not going to go all the way to infinity. The other thing that is important to realize is that if we treat the series as discrete or as continuous, it will also lead to different results. So here we have the basic idea for a Fourier series for two waves. We have these two sine waves here, and they are slightly out of phase. And here we have the summation of these two simple waveforms here. Okay, so we can think that we have, if you consider this time, okay, here we have the amplitude for this upper wave. We have the amplitude for the middle wave, and they will be adding up, and the resultant wave will have a larger amplitude. So there are times that these two waves, the upper and the middle, will add up, and the times when they are not going to add up. So we have this particular time here that basically they're not going to add up. So the Fourier transform and spectrum. So what is the Fourier transform? The Fourier transformation is when we go from the space that is expressed as a function of the argument t or tau, okay, of the data series, into a space that is spanned, that is generated by frequencies. So that's the frequency or spectral domain. So this transformation that transforms from tau to f, from the argument tau time series to frequency, is known as the Fourier transformation. And this transformation will give us the amplitude or the spectral power of the frequencies that compose the data series. And the representation of this is the spectral power, or simply the spectrum, is known as the Fourier spectrum or periodogram, or simply the spectrum. So we have here this example, which is example that I generated. I essentially added 4 different waves, and with different amplitudes, different frequencies. And here is the original wave. I'm calling it a time series, going from 0 to 500. You can think of hertz, for example. Here is the amplitude, and the unit here, it's we can think of meters or whatever. What happened is that this is the time frequency. Okay, so this is in time domain, okay, or observation domain. And now we have here the spectrum, which is in frequency domain. So what we have here now is the horizontal, the vertical axis shows the spectral power. So this is the power that each one of the frequencies has. And we can see that we have 2 frequencies around 50 hertz, and 2 other frequencies around 100 hertz. So so this is it. This representation A is the same as representation B. Okay, they are just happening in different spaces. Okay, so we are looking at the same thing from a different perspective. Here is L over tau, and here is the power over frequency. Now, I mentioned to you that we have these issues of the length of the time series. Okay, so if we have an infinitely long data series, the peak of the periodogram would indicate the frequencies that contribute most to the analyzed data series. Okay, so if it is an infinite time series, we basically have, we can detect very well the frequency. So it is going to look like a spike. Now, for data that is finite, which is usually the case, but the shorter the, well, how can I say that? The less finite the data is, we are going not to see a spike like that, but we're going to see like well, look like a Gaussian function. So in this case, what happens is that the detection of the actual frequency, it becomes less certain or more uncertain. So this is a problem that we have, the distortions in the periodogram that will happen depending on the size of the input data series. Now, there is one issue that is very interesting and very important for us to understand. That is called the aliasing. And aliasing is basically represents, well, it's going to represent a wrong sampling, or the effect of a wrong sampling. So let's consider this a simple sine wave here, and we have the peak-to-peak defining one cycle. And let's suppose that we are sampling this wave, the sine wave, using a sampling rate that corresponds to 3/4 of a cycle. So the first sample will be here, the second here, the third here, the fourth here. What happens is that if we then join these points, we're going to have a different function. Okay, so because the sampling rate is not appropriate. So to solve that, a Swedish guy called Nyquist came with what is known as the Nyquist theorem. And he introduced the Nyquist frequency, or the folding frequency, that relates the sampling of a continuous function or input signal to derive a discrete sequence to avoid aliasing. Okay, so we want to have the Nyquist frequency is going to be a minimum frequency that will allow us to retrieve the function, okay, without having that misrepresentation that we call the aliasing. The value of the Nyquist frequency is half of the sampling frequency, So this is basically Nyquist frequency, the theorem. But we will be actually working with the so-called sampling frequency, or the sampling rate, which is going to be Fs, should be at least twice the highest frequency we are interested in. So this is the frequency, the sampling frequency, or sampling rate. There has to be at least twice the highest frequency that we're interested in. We may have, we will have time series that have lots of different frequencies, but we may be interested in detecting in sampling just up to a certain frequency. So if the frequency, the sampling frequency, is equal to 2 times omega, omega is a frequency here, 2 times omega, then all frequencies less than omega will not be aliased. Okay, so that's important. So let's look at an example here, applying these Nyquist or Nyquist theorem. Example, sampling a 1 Hz sine wave signal with a sampling frequency of 2 Hz. So what we are doing, we're using twice, the sampling frequency is twice the highest frequency. So we have here then the wavelength of the original signal, and here we have the sampling rate. So which means that if we sample at these points in here, we are going to be okay. Actually, if you sample anywhere with a half a cycle, and then we fit a function to the sample, we are going to retrieve the original frequency. Well, not all the time. So the Nyquist frequency represents the maximum frequency that can be represented given a particular sampling rate, and the Nyquist rate is the sampling rate required to prevent aliasing. So the Nyquist rate refers to sampling rate. So why do we mention that one has to be 2 times the other. So the frequency, sampling frequency, the highest frequency, it has to be well, at least equal. But as a matter of fact, it is better to be slightly larger. So because we may have a situation where we're satisfying the Nyquist theorem here, but the position of the samples will actually retrieve a straight line. Okay, so that doesn't really help us. That's why we always should use the sampling frequency slightly larger than twice the maximum frequency that we want to represent. Okay, flat spectrum and white noise. The spectrum of residuals, or the random noise, is constant. It is a flat spectrum if the residuals are statistically independent. In this case, the random noise is said to be white noise in the sense that it is exactly the same in all frequencies. Okay, so the term white comes as an analogy with the white color, because the white color is composed of all colors. So the white noise in here means that we have all frequencies. So if it has all frequencies, like having all colors, it means it's white. So this is the flat spectrum, amplitude over frequency, and it is flat. It means that every frequency, okay, at every point we have the same frequency. That's called white noise. Now, if that doesn't happen, we have colors. Okay. So what happens if some frequencies are missing, or if a color is missing? If we have all colors, but then suddenly the blue is not there, so which means we're not going to retrieve white anymore. So we have what is known as the colored noise. So you're going to hear people talking about colored noise, and again, the analogy is with the light. Okay, this is the electromagnetic spectrum. It shows everything. Of course, the color, we are talking about the visible spectrum, but I'm showing here everything because you can see if we go towards red, we have a low frequency, and if you go towards blue, we have higher frequency. So people say then that, oh, we have a red frequency or a blue frequency, a red spectrum, or we have a more properly, more commonly people say we have a red noise or a blue noise. So red noise, we have larger wavelength or lower frequency, and the blue noise, not blue nose, blue noise, will have a higher frequency. Okay, now let's talk about the transform. Because what we have is we have a time series, tau, and then we make a transformation to obtain the spectrum. Okay, the spectrum is going to be now the power as a function of frequency. So transform is an operation that will do that. And here I'm giving an example of a transform to understand that it's essentially a different way to look at the same quantity from a different perspective. So let's consider that we have this problem here. We have this division, y equals to x over z, And the usual way that we can do, of course, you do the longhand division, and we obtain the problem, okay, the solution to the problem. Alternatively, we can do a transform analysis in which we transform our problem, y equals to x over z, we transform into a logarithmic expression. So we are going to look at the same expression from a different perspective. So the log of the summation represents the product of the division, represents here the log of the subtraction. We are subtracting the log of x and the log of z. So log of y equals to log of x minus log of z. So which becomes now easier because we can get the log of x and z, and we just subtract both of them, and then which means that now we have the log of y, and everything you have to do is inverse transformation. So we use the anti-logarithm table, and now from log of y we retrieve the value of y. Okay, so this is a transform. Okay, and I'm going to show you the transform as we usually express it, but the simple idea of a transform is that we are essentially looking at the same thing from a different perspective. So this is the interpretation of the transform. In our case, we have a waveform which is being defined from minus infinity to plus infinity. This is important because of how the spectrum will look like, the finiteness of the data. Remember that we mentioned that. So this function is actually the summation of two different signals. Okay, we have the signal here, number 1, and we have the signal number 2. So if we add them together, we obtain our input signal here. So the Fourier transform will transform this time series into a series of power per frequency. So what we have now is we have the two representations, and usually it comes like that because we have a real part and a complex part. We usually just are going to work with the real part, but it's important that it's a transformation, the complex number, and so this is it. We have one frequency here, okay, and we have a lower frequency. We have a higher frequency, and what happens then is that we have here is the higher frequency, representation of higher frequency, and here we have the representation of the lower frequency. Here's a representation of the Fourier transform. I'm not making derivation here. I will make available for you another presentation that goes a little bit deeper on this. But it actually, if you look at it, is okay to understand. It is a very simple equation. It may be intimidating because we have complex numbers, but it's actually simple to understand. So what we have here is essentially the Fourier transform. This is the function of frequency. Okay, so that's the spectrum or the periodogram, and what we have here, g over t, g of t is the time series, okay, or the function that we are representing. So we have a integral over the input signal, and it's integral because we are sampling at every possible point. Okay, so it's a well, differential small sample interval, and making it from minus infinity to plus infinity. In practice, of course, we're going to deal with finite series, and the issue of the finiteness will play a role depending on whether the input signal is short or it is very long. So we can say here that we have the original signal time series, okay, and the other term that we have, so it's an integral of only two terms. The other term is the Euler formula, which essentially is giving us the rotation in a complex plane. Okay, so the product of the original series by the Euler formula, and this is happening at every single point, is going to basically retrieve a value for the frequency. So if there is no power in a particular frequency, and here we have the Euler is a function of 2 pi, of course that's the circle, the I f is the frequency, t could be the argument on the signal. So every time that we make this product is going to result in a value that is going to be either small or large, and if it's small means that for that particular frequency there is no spectral power, and if it is large it means that that particular frequency will have a large spectral power, so it is an important frequency. So what we have now, this is the infinite sampling, of course, and G of f is the Fourier transform signal, this spectrum. One thing that I'm doing is I'm providing the link in the description of the video to two external videos which I found very nice. One talks about aliasing, and the other one, it's a beautiful video that looks at a geometric representation of the Fourier transform. It's beautiful. Okay, so the author managed to have a very nice representation looking at the input signal and its representation in frequency domain. So I would recommend all of you to watch both videos. We are going now to look at a series of Fourier transforms. We go from time domain or observation domain to frequency domain. Okay, and we start with a pulse form which has a characteristic that it is finite, and we know when it's finite we don't have a spike for the frequency. We actually are going to have something that looks like a sinusoid, and what this pulse here represents, okay, is basically the summation of several different waves, and that's why we have different frequencies in here. Okay, and we have more frequencies, but they are so small now that doesn't matter, really doesn't matter, they're not going to show up. Um, Now let's look at an example of something similar, but that will have a longer length. A Fourier transform of a square wave. Now this is interesting because this is a square wave. What is a square wave is essentially the summation of lots of different waves as they will be added on top to each other. They are going to resemble this square wave as the series grows to infinity. So this is the spectrum of the square wave, okay? And here on the upper part and in the lower part, we can see the spectrum of a function that is trying to approximate a square wave. Okay, so we can see that in this case we are retrieving just basically two frequencies. We have two frequencies, these low frequency, and then we have the other one here. As they are added, we go to this form here. Now we're adding one more. Okay, so what we have this line represents the summation of these two terms, and what we have now, we are adding a new term here, a slightly higher frequency. Okay, the result, it goes into here, and again it is getting closer and closer to a wave function. Now we have this new frequency here. Now we are getting all the three here, S2. Now this is S3. This is these three frequencies plus this other one. The other one is even a smaller frequency. Sorry, higher frequency. So it goes approximating the square wave function. We have one smaller frequency in here. Okay, and we can go on these for a long period of time until we essentially approximate the square function. Okay, so other time and frequency domain representations. We have this input that looks like a triangular shape, and this is the representation frequency domain. This is a cosine representation of a finite time series, and we have this is the representation, and again we have the real and complex representations. Because of the finiteness of the time series, we have something that looks like a Gaussian representation. It's not a spike. This is a what is that? A sine wave for this particular. Well, this is an expansion that is represented here as a sine wave. Okay, so this is what we have. So there are a few examples here which are interesting. The cosine plus a constant term. We have an exponential function. We have now exponential with a quadratic term. We have this box function, finite box function. This is a sine function that will, in this case here, it is represented as a box. Okay, well, what we have in here is as follows. We have these box function. This box function here, we retrieve a sine function. Now, if we make the input as a sine function, we retrieve a box function. Okay. So we made we are, of course, these arguments are different, but it shows something interesting here. A constant function will have just one frequency, and we have additional terms here. This is again the constant function will have one frequency, and this is for a spike, and that will have these flat k times delta t. So these delta t okay. So anyway, we have here a few representations of time series and frequency domain representations. What we are going to do next is we're going to work on an example using MATLAB on how a way of doing filtering in frequency domain. Oh, we have more here representations, a cosine and a sine. These will be growing towards to infinite because we have spikes here. Okay. Okay. Yeah. So what is filtering in frequency domain? So consider that we are given a time series. Okay, and this is the time series we're going to work in our example. There are different waves in here added. Okay, we do the Fourier transform. So this is the L over tau, or of tau. This is L over F, not over, of F. And so what the spectrum is giving us the position and the power of different frequencies. Okay, and let's suppose that we want to apply a low-pass filter. Low-pass filter means that we are only letting the frequencies that go through the filter are the low frequencies, so it's a low-pass filter. In which case, we have to eliminate this frequency here, and that's what we did. We just, you see here, we basically added zeros in the value here. Okay, so we eliminate this frequency. And we do the inverse transform. So this is the Fourier transform. This is now the inverse Fourier transform. The Fourier transform, we go from observation domain to frequency domain. The inverse Fourier transform, we go from the frequency domain. Let me put these L prime here because we just added zeros. We eliminated the high frequency, and now we have, well, let me call this L prime of t, of tau, and here we have representation of only the low frequency. Okay, so this is basically the idea of filtering in frequency domain. Okay, so the original time series is then represented in frequency domain. We will eliminate the unwanted frequencies, and after eliminating the unwanted frequencies, we go back to the observation domain. Okay, so we are going to work on this example next time.